Hello everyone, my name is Feng from Tsinghua University, and today I'm going to present our work on enabling in-situ programmability in network plan from architecture to language. Switch chips have evolved from fixed function switches to programmable switches, and users can write their own packet processing functions. With the emergence of more and more diverse network applications, it is necessary to update the functions of the switch without interrupting the current traffic. That is, give users the ability to customize the protocol, vertible, and processing logic at runtime. There are many scenarios that need the feature of in-situ programmability. For example, network telemetry or measurement based on real-time network conditions cannot be foreseen at design time, so it is better to make them on demand at runtime. Second, many in-network computing functions are not always needed and are resource-consuming, so it is better to make them hot pluggable at runtime. Thirdly, the change of traffic pattern and network scale makes it necessary to enlarge or shrink a table's width or depth, provision new tables, or change a search key at runtime. Fourthly, for multi-tenant services, modifications for any tenant cannot affect other tenants. By now, the service upgrading needs to stop all services. Lastly, device updates can be destructive to the states of stateful functions, for example, congestion control and caching. This can be avoided by uninterrupted incremental updates. So as the popular implementation of this plan, what limitations does PISA have in terms of implementing in-situ programmability? As for protocol, in the figure, four functions need different protocols, and the front parser is decoupled from the pipeline. So when adding a new function with new protocol, the front parsers and the pipeline stages both need to be updated, which can be rather complicated and time-consuming. More seriously, we're unable to add new protocols to parse in PISA, as the fields in the protocol should be orchestrated meticulously at design time in PISA. In PISA, the maximum number of ingress and egress stages is fixed and they are hardwired, so the design space is limited. For example, if one needs n plus 3 stages for ingress processing, PISA cannot allocate them. At the right figure, inserting a new function f3 between f1 and f2 requires to reprogram all the affected stages. After deleting f1, two empty processors are left in pipeline, which influences the latency. As for memories, when adding or deleting functions, processing logic migration means the associated table migration, which is time-consuming and error-prone. And if the size of the flow table is big, there should be more than one processor to implement the function, which decreases the usability of MAUs. So we propose IPSA to solve above problems. Specifically, we use distributed on-demand parser to implement protocol updating, template-based stage processor to implement processing logic customization at runtime, virtual pipeline to improve the flexibility of the original pipeline, and disaggregated memory pool to add, recycle, and modify flow tables at runtime. We integrate the front parser into the normal pipeline. The function model parses protocols that it will use independently. Naturally, PHV in PISA is not used in IPSA. IPSA uses packet window to parse protocols in time, along with processing packet. And when inserting a new function, this architecture can minimize the effect on other functions. Naturally, the processor is not match action unit anymore, and it is composed of parser to pass protocols out, matter to match fields against 4 tables, and the executor to execute actions. We use the parser match executor triad as a template skeleton named TSP. For example, in PISA, we should download the binary executable file for the chip, but in IPSA, we have already downloaded the skeleton into the chip. So configuring the processor becomes downloading skeleton parameters: what to pass, which table to look up, and what actions to execute. Like POF, all above are based on offset and length, so the processing is independent of particles and fields. For example, if we want to use the head of length field IHL in IPv4, we should obtain it by IPv4 offset, the internal offset of IHL and the length of IHL. We choose an interconnection network to connect all of the processors, so any 2 processors can be neighbors, different from the hardwired pipeline in PISA. In the left figure, the pipeline is 1, 4, 3, TM, and 6. And now we want to insert function in TSP2 after TSP4, so we can modify the configuration of the interconnection network by adding TSP2 to the pipeline to support the new function chains 1, 4, 2, 3, TM, and 6. What we should know is that the interconnection network acts as configurator, not scheduler, as we should ensure the throughput by full pipeline implementation with no access contention. As for memory, recycling and rebuilding lookup tables are tough problems. IPSA disaggregates the memory from processors to a shared memory pool, like DRMT. A crossbar switch is statically configured for each design to provide interconnection between TSPs and memory blocks. Updates on either TSPs or tables may require a reconfiguration of the crossbar. Also, there's no scheduling problem. To cope with the scalability, different crossbar types, such as segment crossbar, closed, bins, and etc., can be used as a trade-off between flexibility and resource consumption. An incremental memory and TSP allocation algorithm can be seen in the paper. We use big bubble updating technique to update the pipeline. For example, TSP3, TSP4, and TSP5 should be reconfigured at runtime. Firstly, TSP2 is stopped from moving packets to TSP3 to drain TSP3 in T clock cycles. After that, demo clock cycles are used to configure TSP3. Then the packet flowing resumes. The other TSPs, such as TSP4 and TSP5 that need to be modified, will take turn when the created bubble arrives. At last, with packet flowing, the front buffer is empty again. The buffer needed for updating is less than 1% memory in terms of the switch buffer. With big bubble update, we can ensure that any packet is processed either by the complete new configuration or the complete original configuration. So the updating consistency is guaranteed along with the update process. We extend P4 with RP4 to support in-situ programmability for users. The workflow of RP4 is, firstly, user customizes the base design in P4. Then, with the RP4 front-end compiler, it can be translated into RP4 intermediate representation. In the meantime, the RP4 FC exposes runtime configurable API to the control plane. With the RP4 backend compiler, the AR can be compiled into target-dependent configurations. In-situ programming can be done in IPSA control plane. Users can download commands and RP4 code snippet and the RP4 backend compiler translates the runtime requirements and updates the RP4 error. Then the compiler provides new interfaces for flow entry modification and so on. The corresponding implementations can be seen on the open source website. We use the level 2 switching and the level 3 routing as the use case. L2-3 stage determines whether the packet goes to level 2 or level 3 forwarding. The max stage does level 2 switching, and the IPv4 stage does level 3 routing. ACL filters permitted control. Now, users want to add MPLS function to the switch. They can write commands with RP4 snippet, and the controller can compile the updates and download them into data plan, such that L2-3 compares Ethernet protocol, and MPLS compares MPLS protocol and can both push or swap the label. Then ACL compares IP and TCP protocols out. So the MPLS is inserted into the data plan. In the evaluation with the 12 processor configuration, IPSA spent 12.09% more LUTs and 9.69% more FFs, as there should be more spaces to store the configurations. As for throughput and latency, in the Xilinx FPGA, PISA can reach a frequency of 153.30 MHz, and the IPSA is 110.45, as IPSA is limited by the multi-die architecture in FPGA, which can be solved in ASIC chip and 3D IC techniques. In the left figure, the longer latency of the IPSA per type is due to field and floatable profile fetching, match key assembly, and primitive loading. As for IPSA average pipeline latency while updating, we can see that the packet processing latency is relatively steady during updating. As for the update performance, for updating compiling time, IPSA only compiles the updated code segment, so it takes much shorter time than PISA. Secondly, unique to IPSA is the parameter loading time. Thirdly, as we use Big Bubble Update, IPSA's pipeline haunting time is only 0.34% of PISA's. In summary, PISA's overall time is 4 orders of magnitude smaller than that of PISA. To summarize the paper, firstly, IPSA is proposed and is verified in theory and FPGA implementation to support runtime reconfigurability in terms of protocol, processing logic, and flow table. Secondly, RP4 is extended from P4 to support user to reconfigure data plan at runtime. The behavioral model and the corresponding compiler is open source. We provide the researchers a new target to deploy their applications and support runtime reconfigurability. Please contact us if there exist problems when using the target. And now, we are working on providing users with GUI to configure data plan more intuitively. An IPSA demo can be seen in the poster session. Thank you for your listening.